So, hello dear friends. In the previous lectures, we have studied about Lorentz transformation equations for displacements and time, then mass velocity relations, then energy and mass relations. So, in the present chapter, we will study the transformation equations for linear momenta and energy. So, here we assume that we have a frame of reference S which is at rest, and another frame of reference S dash, it is moving with velocity v along the positive x-axis. So let we have a particle having rest mass m naught, and let it is moving with the velocity u in S frame of reference, and we suppose this velocity have components ux, uy and uz respectively along the x-axis, y-axis and z-axis respectively. These are the components of this velocity u vector. Then applying simple magnitude formula, u square, it will be given by this relation. We mark this equation number as equation number 1. Let particle has mass m. It is the moving mass in S frame of reference. So applying mass velocity relation, m, it will be given by as the velocity of the particle we have taken now. When we see the same particle from S dash frame, which is moving frame, then we assume it has velocity u dash vector in S dash frame of reference, and it is having components ux dash, uy dash and uz dash along x-axis, y-axis and z-axis respectively. So the similar formulas for equation number 1 we have for S dash frame, it will be and moving mass in S dash frame as so now we have masses in S frame, S dash frame respectively, velocities in S frame and S dash frame respectively. Now we try to correlate the velocities first, then momentas. So according to transformation equations for velocity, ux dash, it will be equal to ux minus v. So these transformation equations we have derived in our previous lectures. So we mark these three correlations between the components of velocities in S frame and S dash frame respectively by equation number 5. So dear friends, as we know, momenta, x component of momenta in S dash frame is given by momenta along x-axis, mass into velocity in S dash frame. So we have taken the mass of the S dash frame particle in S dash frame, velocity of the particle in S dash frame. As we are finding the x component, so we have taken the x component of velocity, so it gives us x component of moment. So now we are to just substitute the values. M dash from equation number 4. Here I will show you the equation number 4. This is equation number 4. This I have written here into ux dash from equation number 5. So we mark this as equation number 6. So now our aim is to calculate this term. We will try to solve this term. So if you look carefully at this term, but what it does contain, it is u dash square. U dash square we have written here, u dash square. Here we put value of ux, uy, uz from equation number 5 respectively, square them, add them, and we convert that into this very term. So this will be our next task. So from equation number 3 and 5, u dash square, it is ux square uy square u z dash square so u dash square it will be. So we will take the LCM. Square. So first term is, so look at the second term. This will be common. When we square, there will be no square root. So we mark this as equation number 7. We make a little more simplification as well. As u square, it is equal to ux square plus uy square plus uz square. So this we can write as u square minus ux square. So we substitute this value here. So it will be like we make this as equation number 7. So now what we actually need, our requirement was this term 1 minus u dash square over c square. So from this we try to find. So take U dash square is this term. C square is from here. Now take the LCM. Minus, so sign changes. So now open the brackets and solve. So we need a few simple mathematical steps. These are easy ones, you can do yourself. Just follow, do yourself and follow the steps. I will write the next term here. So now open it. C square, C square, change the sign, change the sign, this cancels, this cancels, this cancels. So what we are left with? C square minus V square minus U square V square over C square. So from this we take common C square minus U square so this will be so taking the square root, take square root both sides, so we will get this so we need one little more simplification. So for that we will do square root, it is equal to, I will show you, here we take c square common, and out of the square root 1c comes, so it will be so this cancels. So we make this as equation number 8. So now we have this term. So now we will put this term in equation number 6. This we want to calculate. Now we have drained this value. We substitute it here and we will get px dash. So from 6 and 8, px dash, it is equal to m naught divide by that term, this very big term, this goes upside, this cancels, so we are left with m naught 1 minus u square over c square ux minus v 1 minus v square by c square. What is this? This is m. This is m. We supposed this is m in equation number 2. So m so we can write it mux minus mv 1 minus v square by c square square root. So mbx is px, mux is px minus, as we know, E is equal to mc square, so m is equal to E upon c square. So in here it will be E v by c square 1 minus v square by c square. So this is the first transformation equation for x component of momenta. So on the similar lines, now we will try to derive other components as well. So for that, y component of momentum in S dash frame of reference so m dash uy dash I will show you the previous equations that we have used. M dash from this relation and uy dash from this relation. So what we will do, we will substitute this value as we have done for x component of momentum, cancel out the terms, and we will get the formula for py dash. This term will be This term is reverted, goes in the denominator. It is cancelled. This is cancelled. This is M. What is this? This is Py. So our next term will be calculate the Z component of momentum. For the Z component of momentum, calculation is very easy. You can do it here as well. Change Y by Z, because the equations for Y and Z components for velocity, they are similar. This. So dear friends, this completes our first part of this section, the transformation equations for momenta. So now we try to derive the transformation equations for energy. So let E dash is the energy of the particle in S dash frame. So it will be equal to mc square. So from equation number 4, this term be calculated. Now you might be remembering this term because we have used this term now many times. So what this term will be? It is m. We take c square forward. So the equation is so open the bracket. C square cancels. So this is E. Mass into ux, m into ux, it is px. So this is the transformation equation for energy. So dear friends, now we have derived the 4 equations, 3 equations for momenta and 1 equation for energy. So now we write these equations collectively as direct transformation equations that we have derived, that is px dash px minus ev by c square py dash pz dash e dash these transformation equations correlate the parameters of S frame to S dash frame. So now for inverse transformation equations, we simply change V to minus V and we will get the similar 3 equations for Px, Py, Pz and E. So it will be Px dash Py dash Pz dash So this is a similar technique we have used for Lorentz transformation equations, Galilean transformation equations, and so this completes our topic for transformation equations of energy and momenta. So dear friends, don't forget to see my next lecture that will be related to the numericals. We will solve few numericals based on these transformation equations, either involving direct transformation equation or involving inverse transformation equations. So kindly share and subscribe my channel. Thanks a lot.